The purpose of this video is to give a short overview of section 14.5 in the textbook on vector-valued functions. So a vector-valued function is essentially a triplet, we'll call R of t, which is a map from R1 to R3. So for instance, you can think of this as being the x, y, and z values of some trajectory as a function of time. The author Greenberg actually defines the derivative in terms of finite difference of the vector. So Greenberg says that the derivative d by dt of r is he defines it in terms of the finite difference as usual, is the limit of delta t goes to 0, r evaluated at t plus delta t minus r evaluated at t divided by delta t. So again, he defines that in terms of the finite difference. You could also alternatively define it, and we can show that it's equivalent. I would rather define it as dr dt. You can just take the time derivatives of the individual Cartesian component. So when I just have a tuple, sometimes I'll call that a Cartesian representation of a vector. And so this is just the time derivative of x, time derivative of y, and time derivative of z. Those definitions it's easy to show they're equivalent and they're completely interchangeable. Then Greenberg goes on to state a bunch of rules. So if you multiply a vector function, let's say u, so this is theorem 14.5.7, which comes in many parts. So the first part of that theorem says that if I have a scalar function f and I multiply it by a vector function u, which also depends on time, if I want the time derivative, so clearly that's also a scalar times a vector is also a vector. That's clearly a vector function. It turns out that this is just f dot times u plus f times u dot. So the normal product rule works. It's trivial to prove that. You can just expand things in terms of the Cartesian definition and go one element by one element. There are several other properties. I don't want to list them here. I just want to point out that it is not difficult at all to prove those. So this has been a very brief lecture note on curves in section 14.5 and time derivatives of curves.